Well, we're in the last section of this unit. Happy Monday, everybody. Glad you're here. I can see that you're a little tired. It's been a long, great weekend. Okay, so here we go. We are talking in section 6.5 about exponential and logarithmic equations. So we're going to round out our unit here, just solving some more equations. So the first two problems on this page are a review of something we have done previously, solving these first type of exponential equations. And these are the type, remember, where we can equate the bases. So exercise 1 is what I would consider to be a relatively simple version. So I want you to get started with that. And then exercise 2, when we get there, I would consider to be a moderately hard problem. So let's do exercise 1, equate those bases to determine what the value of x is. All right, so just to refresh your memory on this first type of exponential equation, we were able to do these with the algebra tools we already possessed. And so what we're going to do is equate the bases. So this on the left side, the reason I consider this to be a fairly straightforward problem is because on the right side, I've already got this in base 3. So there's nothing to do on the right side. What I need to do here is rewrite 81 with a base of 3. So we have 3 to the x minus 2 power, and then 81 is 3 to what power? Perfect. Thank you very much. 3 to the 4th power. And then just to remind you, the reason we can make this next step is when we first graphed the exponential function at the very beginning of this unit, we saw that it is 1 to 1, meaning if these values, if these 3 to whatever powers are equal, then that means the powers have to be equal. So I don't even need to worry about the base. I can just now make this next step right here. And then last thing, this is something from introductory algebra eons ago. I'm going to add 2 to both sides, and I get x is equal to 6. And since I have no domain problems with exponential statements, that is my answer right there. So again, these first two problems are review. We talked about these when we first talked about exponential equations. Exercise 2. Okay, exercise 2 is a little bit more involved, just because both powers have binomials in them, and then both of the numbers need to be rearranged for their base. But give exercise 2 a problem, or a try. Just to make sure we're all heading the same direction, what's the base that you can write 16 and 32 in? 2. Great. Keep going. All right, so I'm just going to get started with this. If you have a question, of course, please ask it. I want everybody to do amazing on the test that you have next class over these 5 sections of chapter 6. So 16, I can rewrite as 2 to the 4th power. And then I have 1 minus x. And then 32 is 2 to the 5th power. And then I have x, pen, don't fail me. There we go. X plus 3. Power rule of exponents says that I can multiply those exponents, so I will do that. So I have 2 to the 4 times 1 minus x, so 4 times 1 is 4. 4 times negative x is negative 4x. On the other side, 5 times x plus 3, 5 times x is 5x, 5 plus 3 is 15. Any questions so far? Anything that I've done that makes 0 sense to you? We're equating the bases because we can on these problems. Again, the exponential 2 to whatever power is a 1-to-1 function. So now all I need to care about is the powers. So 4 minus 4x has to equal 5x plus 15. And now I'm just going to go ahead and finish solving this. I'm going to bring my 5x over to the left by subtracting it. So I get negative 9x over here. I'm going to bring my 4 over to the right by subtracting that, and I get 11. Last thing to do is divide both sides by negative 9, and we get x is equal to negative 11 over 9. And there we go. And that is my solution set. Those 2 problems are review. Okay, so I think we did that in section 6.1 when we talked about the exponential. But I'm willing to entertain any questions before I move on to the next one, if you got one. Okay, well, the problem then happens if we look at the next example I have, example 1. How do I now solve an exponential equation like this where I can't equate the bases? Okay, I can't make 7 and 12 a power of some base like 2 or 3 or 5. So clearly I need something different to solve this. And the good news is that there was a lovely property of logarithms that allows us to work this. So I'm just going to remind you, this is the power rule of logarithms, and it says this: if I have the logarithm of any base of x to some power, because that's the problem I have with example 1, is I've got a variable in the exponent, and I need some way to get it out of the exponent so that I can do the algebra I know how to do. Who remembers, because this is what we talked about last time, what does the power rule of logarithms say I can do with this n right here? Perfect. I can multiply my powers because remember the logarithm is always equal to a power. So I can take this power and I can move it out to the front. And so then I get n times the log base a of x. Okay, so this property right here is going to be helpful to me. So for example 1, I start off with 7 to the x power is equal to 12. The key here is that you notice I can't equate the bases, but I have the variable in the power. So here's what I'm going to do. I'm going to take the logarithm of both sides. Okay, I'm going to use the common log, the log base 10, because my calculator has a log base 10 button. That's why I'm picking this. And so I'm going to do the log, the logarithm of 7 to the x power is equal to the logarithm of 12. Okay, so this is one of the useful benefits of logarithms. There's lots of others as you go through math, but this is kind of one of our immediate payouts, is now I can solve any equation that there is a variable in the power on it. So now what I can do is I can use the power rule of logarithms. This x, this variable that I want to solve for, I can move it out to the front. So I'm going to do that. And I have x times the log of 7 is equal to the log of 12. I just want to pause for a minute because I know logarithms are goofy and I know you're new to them, but the logarithm of 7 and the logarithm of 12 are both numbers. You could put those into your calculator and you'll get values for them. They're irrational numbers. I wouldn't recommend it because it makes a lot more to write, but I know they look goofy, but it's just a number right here. It's like having the number 5 or -6. Okay, it makes no difference as far as our algebra. So if I have my variable times a number, it just happens to be log of 7. If I have my variable times a number, what do I do to get the x by itself? you divide by that number. So I'm going to divide both sides by the log of 7. That is something that we definitively can know. It's a value. And so now the log of 7 divided by the log of 7, those things cancel. And I have my x left. And then, let me write this in a better place because I don't really have room. So I have my x left. And on the other side, I have log of 12 divided by the log of 7. I'm going to leave it just like that. That is the exact answer. If you want to get an approximation, you can go ahead and put that in your calculator and get whatever that is. That's fine. And so my solution set looks like this. The log of 12 divided by the log of 7. And there we are. So when I have my variables in the power and I can't equate the bases, the way to approach these problems is now using logarithms. So exercise 3 right next door, it's almost exactly the same thing we just did, slightly different numbers. I want you to apply this property of logarithms to that, please. All right, so I'm going to go ahead and take the log. I'm going to use the common log. The most common ones to use are either the common log or the natural log, simply because your calculator can evaluate those fairly quickly. So I'm going to use the common log. So I have the log of 5x is equal to the log of 19. Again, I'm going to use the power rule of logarithms. I'm going to bring that x down to the front. So I have x times the log of 5 is equal to the log of 19. One more time, I'm just going to repeat for you that the logarithm of 5, the logarithm of 19, those are known values, even though they look kind of scary. So I can now just divide both sides here by this value. And so what we all should be looking at and what our solution set is the log of 19 divided by the log of 5. Questions about what we've just done? I know you all are feeling very shy today. I get it. Okay, so what we're going to do next is the same thing. The only difference between my example 2 and example 1 is I'm going to employ a little bit of my basic algebra that you came into this class knowing. So again, I just want you to keep repeating to yourself. I don't want you to be intimidated. The logarithm of 5, the logarithm of 19, the logarithm of 7, the logarithm of 12, these are just a value. Okay, there's nothing mysterious about them. So for example 2, here we go. Again, I notice I got a variable up in the power, so I am going to take the logarithm of both sides. That is my Q. So I've got log to the 2 to the x plus 3 power is equal to the logarithm of 5 to the x power. Step 1, take that logarithm. All right, what step 2 is, and so my step 1, my step 2 are always the same. So step 2 is now I'm going to bring that power down. So I'm going to bring this x plus 3 down. I'm going to put it in parentheses because it's that whole thing times the log of 2. And on the other side, I'm going to bring that x down, and it's x times the log of 5. Okay, at this point, you have done all the new stuff. Okay, the rest of what follows here is just basic algebra. We're going to do a little distributing and a little rearranging of my terms. Okay, I know I'm repeating this. You might get tired of it. That's okay. I'm the one talking. This log of 2, this log of 5, those are just numbers. Okay, they're not variables. There's nothing unknown there. The variables are the x's. So the first thing I'm going to do is I'm going to distribute this number, this log of 2. So over here, I've got x times the log of 2 plus 3 times the log of 2 is equal to x times the log of 5. At this point, if this was just any equation you've solved before in your life, and it looked something like, you don't have to write this down. I'm just trying to draw out of you that you already know how to do this, even though it looks a little more complicated. So like over on the side, if this was the equation, 2x plus 9 is equal to 5x. Pens had a long weekend too, apparently. They don't want to work. All right, there we go. If it was 2x plus 9 is equal to 5x, I don't have any logarithmic numbers here. What would you do to both sides? What would your next step be? Yeah, you'd get the x's on the same side, right? You'd subtract the 2x. Okay, well, that is the same thing that we are going to do here with this problem. I've got two terms that have a variable, have an x in them. So I'm going to get all of the terms with the x on the same side. Now the problem, or what seems like a problem, maybe a little bit of stress, is they're not like terms, right? The log of 2, the log of 5, I can't subtract those and get the log of 3. That's not how logarithms work. So we have to approach this a little different. So let me go ahead. I'm going to write out the step. I'm going to be very thorough here. I'm going to subtract the x log 2 from both sides. And when I do that, on the left-hand side, those x log 2's cancel, and I just have 3 times the log 2. It's just sitting there waiting patiently. There's nothing else going to happen to that 3 times the log of 2. Now, on the right side, since those are not like terms, I'm just going to write x log of 5 minus x log of 2. It's a lot of writing, I know. It's inconvenient. Again, we're drawing way back to our introductory algebra days. When I have the same thing in two terms, what can I do with that thing? If I have an x in both terms, what can I do with that x? I can factor it out, yes. Okay, because it doesn't do me any good to have two x's I'm trying to solve here. So what I'm going to do now is I'm going to factor. And when I factor that x value out, I just have the log of 5, which is a number, minus the log of 2, which is another number. I've got one more step, and then we're done with the problem. My point here to you is that all the new stuff with logarithms were the first two steps, taking the log and then using the power rule. The rest of this is just some goofy looking introductory algebra. The last thing to do now, I have x times this value that's in the parentheses. So I'm going to divide both sides by this value, log of 5 minus log of 2. And here's my answer, which I'm going to be real lazy here. And I'm just going to write my solution set on the other side of the x. So I've got 3 log of 2 over log of 5 minus log of 2. We put some squigglies around that. And there's my solution set. All right, so I'm going to ask you to do this twice. We're just going to practice this algebra. So exercise 4, it's very similar to what we've just done, just slightly different numbers. Give it the best try you got. I'm going to get started with the first couple steps. I know that the algebra is involved here, so if anything arises that you're confused about, please do not hesitate to ask me. You're not an interruption. You're the reason I'm here, so I want to answer your questions. So first thing, again, the first two steps are the new bit. I'm going to take the logarithm of both sides. So I'm going to have the logarithm of 4 to the x plus 1 power, and that, excuse me, that's a minus 1. Let me read properly. Minus 1, and that's equal to the logarithm of 7 to the 2x power. Going to use the power rule of logarithms that we talked about last time. So I'm going to bring this x minus 1 down to the front of the log of 4, and then the 2x down to the front of the log of 7. So far, we so good. Has anything gone on that anybody is disturbed about just yet? Okay, so now what I'm going to do is I'm going to distribute. I'm going to get all of my x's on one side, and if there's any other numbers, all the numbers on the other side, and then I'll divide. So distributing, I've got x times the log of 4 minus 1 times the log of 4, so just minus log 4. On the other side, 2x log of 7. Again, is that bothering anybody there? Just some distributing. So this is an equation. I've got to get all of my x's on one side. I don't have any other stray numbers. I only have this negative log of 4, so there's nothing else to really do with that. So I'm going to subtract the x log of 4 from both sides. When I do that, I have negative log of 4. I'm just going to bring it up here so I have a little more room. Negative log of 4. And then again, these two things are not like terms. I can't smush them together, so don't even try. So I'm going to have 2x log of 7 minus x log of 4. Again, and if you got a question, please ask it. I'm on my last step here, so we're almost done with the problem. So if there's anything that's arisen that's bothering you, let me know. The last step is I can't solve if I have an x in these two terms. My whole thing is I want to get the x all by itself. So the way I do that is I'm going to factor that x out. So I have a negative log of 4 on the left. I factor the x out, and I'm going to have 2 log of 7. That's just a number. Minus log of 4. That's just a number. That's good. And then the very last thing is I'm going to divide both sides by this junk in the parentheses. So I'm going to do that, and I get x is equal to the negative log of 4 over 2 log of 7 minus log of 4. Again, I'm going to be a little lazy. I'm just going to put that in squigglies, and then I'm going to make a little note for you here. That's the correct answer. And when you take the test Wednesday, you can leave the answer just like that. But a My Math Lab tip, I'm pretty sure somebody mentioned to me, taught this class in the spring, that My Math Lab's not going to like this negative out in front. It's going to want that to be positive. So all that means you do is this. You're just going to take that negative, instead of having it in the top, you're going to distribute it in the bottom. So what My Math Lab might want you to put in here is the log of 4 in the top, so now it's no longer negative. And then what I'm going to do is I'm going to flip the signs on these bottom terms. So instead of a negative log 4, I'm going to have a log of 4 minus, okay, so instead of a positive 2 log of 7, it becomes a minus 2 log of 7. Those answers mean the exact same thing. One is, for me, one is not preferable to the other, but for My Math Lab, I think they have a clear preference. So just be careful when you're putting in your answers. Yeah. Okay, great question. So if you didn't hear it, how come I can't cancel the log of 4s? So this again just goes back. Instead of answering it right there, I'm just going to have, like, if I have something like this, if I have x over x plus 7, you can't cancel the x's because this x right here is part of a term. This x goes with the plus 7. These two things go together, all or none. So I can't just cancel this x with that x. That is an illegal math maneuver. So I can't do that unless there was an x over here with the 7 and I could do something to all 3 terms. Okay, so I know it looks real inviting. It's something we really long to do, but because this log 4 is a term, it is attached to this by this subtraction. So those two things go together. You can't just cancel part of a term. Awesome. Great question. I'm really glad you asked that. Thank you. Okay, exercise 5 is very similar. So go ahead, take exercise 5 as far as you can, and then I'll begin working it in a little while. Same sort of thing. All right, I'm going to begin this problem. Again, the hardest part of this problem, I think, in my opinion, the hardest part of this problem is the algebra you have to employ to solve for x. My first step, since my variables in the power, I've got to take the logarithm of both sides. So I have log of 2 to the 3x plus 1 power is equal to the log of 3 to the 4 minus x power. The next step is just taking advantage of the power rule of logarithms. I'm going to bring both of these powers down. So I have 3x plus 1 times the log of 2, which the good news, the log of 2 is just a number. And then I have 4 minus x times the log of 3. And again, log of 3 is just a number. So that takes us, that's the new bit. That's the college algebra part of this. The rest of this is just our good buddy introductory algebra, but with these logarithmic numbers. So I'm going to distribute first. So I have 3x log of 2 right here, plus 1 times the log of 2, which is log 2. On the other side, I have 4 log of 3 minus log of 3. The only difference on this problem and the previous ones is I just wanted to give you one that you had both terms with x's and number terms. Oops, I left something off, didn't I? This should be an x. So I'll squeeze it in right there. Sorry about that. Let me make sure that I haven't done anything else tragic before I go any further. Yes, I think we're good now. Okay, so let me repeat. The only difference in this problem than the previous one is you have terms on both sides that involve x's and terms on both sides that are numbers. I just wanted to give you one that had a little bit of everything. And so again, I'm going to do the same thing I did before. I'm going to get everything involving an x on one side. I'm going to choose to do that on the left. I'm going to get everything else on the other side. So I'm going to take this x log of 3, and what I'm going to do is I'm going to add that x log of 3. And I'm going to add it over here to this other x term. That's going to get everything involving an x on the left side of the equation. So let's see what that looks like. I have 3x log 2 plus x log of 3. Now I'm going to go back up, and this logarithm of 2 is just a number. And so I'm going to get everything that's just a number on the right-hand side of the equation. So I'm going to subtract it. And so what I end up with on the right side is I have the 4 log of 3. That's just a number. There's no x's involved in that at all, minus the log of 2. Again, that's just a number. There's no x's involved in that at all. We're almost done with this problem, thankfully. My last step, or second to last step, is I got to factor that x out. Since I've got everything involving an x on the same side, I do that with this express purpose in mind. I can now factor it out. And then the very last step that's going to get my solution is I've got x times this gross looking number right here. And so I'm just going to divide both sides by this number that's in parentheses. So I'm going to do that. So I get x is equal to, the numerator is going to be 4 log 3 minus the log 2. The denominator is going to be the junk in the parentheses, the 3 log 2. Plus the log 3. I'm going to address this because it was asked about the last problem. Hey, Perkster, can I cancel those log 3s and those log 2s? And the answer to that is no, you cannot, because you can't pick and choose terms to go ahead and cancel. It's either all of the top or none of it when it comes to canceling things out. So there's my solution set, and I am done with that problem. Yes. It absolutely does not. So the question, in case you didn't hear it, hey, does it matter? I put all the x's on the right. So maybe you subtract, where are we? Up here. You subtracted the 3x log 2 and got it over here, and vice versa. All that will matter, or all that will do, is in your answer, all of your terms will be the exact opposite of mine. Okay, so in some order, in the top, you'll have a positive log 2 and a negative 4 log 3. And in the bottom, in some order, both of these will be negative. Your signs will be the exact opposite, but it's equivalent. Okay, great question. All right. That is as thorough as I can do about exponential equations. So now we're going to flip to the back page. We may or may not get to all of these problems. There's just some repetition here to hopefully build some learning. I don't want to rush, but we should have time. So the first one at the top, exercise 6. This is a reminder. This is a problem we've already done when we talked about the definition of logarithms. We solved some logarithmic equations using that definition. Perkster, how do I know I can use the definition? That's a great question. When you have a logarithm on one side of the equation, a single logarithm, and a number on the other side, it's just a definition problem. So, good review for the test we're going to have Wednesday. Employ the definition. How do I change that logarithm into an exponential statement so that I can solve this? So go ahead, give it a try, give it your best effort. Remembering the definition, remembering what the base is and what the power and what it's equal to. All right, when I employ the definition, okay, this was the conversion between the logarithmic statement and the exponential statement that mean the exact same thing. What is the base of this statement right here? 5. Thank you very much. 5. What is the exponent? What's the power? 3. The logarithm is always equal to a power. So whatever this is equal to is always the power. And then, so 5 to the third is going to equal the last thing that's there, the 8 minus 3x. So we did problems like this, I think, in section 3, where we defined what a logarithm is. And it was just one of our exercises to get used to doing the definition. And so now I've just got myself a linear equation. So 5 to the third, my calculator will tell me that's 125. I'm going to subtract the 8 from both sides. And when I subtract 8 from both sides, I get 117 is equal to negative 3x. And then I'm going to divide both sides by negative 3. And fortunately, negative 3 does divide into 117. It goes negative 39 times. The one thing to remember about logarithmic equations is whereas the exponential that we did on the first page has no limitation in its domain, if you remember the graph, the logarithm does. Whatever I take the logarithm of has to be bigger than 0. So you always have to plug your value in and make sure that it's bigger than 0. Now this is, when I put negative 39 in, negative 3 times negative 39 is a positive 117, plus 8 is 125. This checks out just fine, but you always have to check. What you're taking the logarithm of has to be bigger than 0. That will come into effect immediately in our next problem that we do. There's my solution set. Now, the only difference between what we just did with the definition and the next 5 problems we do is on the left here, instead of having a single logarithm, I've got 2 logarithms. I have to resolve that. Can't solve it in its present form. But fortunately for us, if we remember our properties of logarithms from the last section, this isn't too terrible to resolve. If you remember, this is just an example of what's called the product rule. That was one of our properties of logarithms. So what I'm going to do on the left side is, instead of having 2 logarithms, to solve this, I'm going to combine those into one logarithm using the product rule. So what I have is, I have the logarithm. It's just the common log because I don't have a little subscript there. It's the logarithm of x times x minus 21 equals 2. Product rule says, remember, when you are adding your logarithms together, as long as they have the same base, you can smush that into one logarithm and you multiply these things together. And that's just what I did. Now, I know you've been in algebra a long time. If you can distribute that all in one step, that's super duper. Okay, no problem at all. But now that's what I'm going to do in the midst of this next step. So if I do too much in this step and you're confused, let me know. But now, since I have a single logarithm is equal to a number, I'm going to employ the definition, just like we did previously. So what is the base of this logarithmic statement right here? 10. It's the common logarithm. When you don't see a number, the base is implied to be 10. What is the exponent of this? 2, yes, indeed. And then it's equal to that junk left over, which I'm going to distribute now. So x times x is x squared. X times negative 21 is negative 21x. And now at this point, it's just, we've done equations like this. It's a quadratic equation. I know that because it's an x squared. So I'm going to get everything over here on the right. 10 squared is 100. So I'm going to subtract 100 from both sides. And so I get 0 is equal to x squared minus 21x minus 100. Quadratic formula always works, but I try my best to be kind and merciful on these problems. So this one's going to factor for us. X squared is x and x. The 2 factors of negative 100 that are going to add up to negative 21 are negative 25 and plus 4. Just going to move this up to the side. So that means either the x minus 25 is equal to 0, or the I don't have enough space to smush it in, or the x plus 4 is equal to 0. So here, if x minus 25 is 0, that means x is 25. Hopefully solving a quadratic equation is not too unfamiliar. This one is -4. Before I celebrate and make my solution set, I've got to go back to my logarithm. I cannot have negatives in my logarithm. So when I do 25, I have the log of 25. That's a positive number. That's great. And then I have the log of 25 minus 21. That's 4. That's a positive number. So this value checks out. Great. The next one's -4. Uh-oh, red alert. My first one, I would end up here with the log of -4. Can't have a negative value that I take the log of. That's not in the domain if you remember the graph. Okay, the graph of the logarithm is, the basic logarithm is all on the right side of the x-axis. So that is bad. So I'm going to cross that one out, and I only have one solution to this problem. All right, so the next problem, exercise 7, is almost identical to what I just did. Now you get to go through the steps. All right, so again, we've got an example of a product rule here. So I'm going to go ahead and combine these two logarithms on the left. That will get this problem in the format that I can solve. I'll have a logarithm on one side, a number on the other. I can then employ the definition of the logarithm. So here goes. On the left, I have the log base 2 of now x minus 7 times x, and that's going to equal 3. That's the property of logarithms. We talked about those last time. If you have any questions about those, please bring them up, email me, do whatever you need to do. I want you to be successful on Wednesday. Now I'm going to use the definition. The base of this logarithm is 2. The power is 3. And on the other side, I'm going to distribute. I'll have x squared minus 7x. So again, in case that looks mysterious and you don't feel like asking a question, all I've done is I've distributed what is right here in the logarithm and brought it down to the next line. It's another quadratic. So 2 to the third is 8. So I'm going to subtract 8 from both sides, and I get x squared minus 7x minus 8. You can use the quadratic formula if you'd like. X squared is x and x. The two factors of -8 that are going to add up to -7 are +1 and -8. So my two answers here, I've got x plus 1 equals 0. And I've got x minus 8 equals 0. In the case of the first one, I subtract 1. You get an answer of -1. In the second one, I add 8. You get x is equal to 8. There we go. Before we celebrate, before we move on to the next problem, I'm going to check these. When I put 8 in, 8 minus 7 is 1. That's a positive number. The log base 2 of 8, that's a positive number, so that one works. Wonderful. The -1, when I put the -1 in, -1 minus 7 is -8. Uh-oh, bad. Cross that one out, and my solution set is just the value 8. Just for reinforcement, we're going to do one more product rule, and then you can see below there's a couple quotient rule problems that gives us opportunity to continue reviewing other things. So do exercise 8, please. I'm going to make the first couple steps. If you're working, keep working. You're going to use the product rule. So I have the log base 9 of x minus 5 times x plus 3 is equal to 1. Only difference on this problem is instead of a distributing, I've got a FOIL, but it doesn't change anything about my process or what's going on. But if you have a question, if that makes it really difficult for you, please let me know. The base of this logarithm is 9. The exponent is 1. And on the other side, I'm going to do this foiling. So when you FOIL x minus 5 times x plus 3, you get x squared minus 2x minus 15. Subtract the 9 from both sides because it's a quadratic equation. The rest of this hopefully is old hat. When I do that, I get minus 24 on the other side. I can factor that. You can use the quadratic formula. It just takes a little bit longer, but it works. The two factors of -24 that add up to -2 are -6 and +4. Setting your two factors equal to 0, your first answer is 6. The second one turns out to be -4. Those are both possibilities. Let's check. When I put 6 in, 6 minus 5 is log base 9 of 1. That's good. 6 plus 3 is log base 9 of 9. That's good. So this answer checks out. When I put -4 in, -4 minus 5 is -9. Can't take the logarithm of a negative or 0. And so that leaves me one answer. I'm just going to keep moving forward. Yes, question. No, that's a really great question. And in case you didn't hear it, if I get a negative, like a -4, can I just assume, well, look back up at this one right here. We got a -39. But when I checked it, there was a negative in there. So that -3 times the -39 gave me a positive, and it worked out. So yeah, it's best to check in case the order of the x's are reversed to make sure. Great question. Thank you so much for asking. All right, so exercise 9. Give that a try. This time it's quotient rule problem, not a product rule problem. Process is the same. Hopefully you remember how to solve an equation that has a fraction in it. All right, just in case you don't remember, I'm going to give you a little less time on this first one, just so that we can run through real quick solving a rational equation. I'll give you a little more time on exercise 10. So there's a minus sign here. That's how I know that this one's going to be a quotient rule problem. So what we have is the log base 2. This time, instead of multiplying these two things, I'm going to divide. So I've got x plus 5 over x minus 2 is equal to 3. Again, going to use the definition of the logarithm. So I've got my base is equal to 2. My power is 3. And then what's left over goes on the other side, the x plus 5, x minus 2. Solving a rational equation, you clear the fractions. So I'm going to multiply both sides by this x minus 2 so that I have no more denominator. So the x minus 2's cancel on the left, on the right. On the left, I've got x minus 2 times 8. So that's 8x minus 16 is equal to x plus 5. I'm going to get all of my x's on the left, all of my numbers on the right. When I subtract the x from both sides, I've got 7x. When I add the 16 to both sides, I get 21. And when I divide by 7, x is equal to 3. All right. Again, let's double check, make sure I'm not taking any logarithms of negatives. So 3 plus 5, that's the log base 2 of 8. That's superific. And then 3 minus 2 is 1. That's positive. So both check out. So I have 3. Exercise 10 is super similar. I am going to give you one little hint. There is a 2 in front of this logarithm. So before you apply the quotient rule, you need to put that 2. You need to apply the power. You need to put the 2 up on the exponent. Then you can apply the quotient rule, but not until you apply the power. So give that problem a try. It's very similar to what we just did. You're going to end up with a fraction. You're going to have to clear the fraction. All right, so I've moved the 2 up. So in case you didn't understand what I meant by that, this 2, since it's out in front of the logarithm, I can apply the power rule of logarithms in reverse. And so this becomes the log base 4 of x squared minus, I didn't do anything to the next one, log base 4 of x minus 1 is equal to 1. Because of this minus sign, I can now apply the quotient rule. So I've got the log base 4 of x squared in the top, x minus 1 in the bottom equals 1. I'm now going to apply the definition of logarithms. So the base of this is 4. The exponent is 1 is equal to x squared over x minus 1. Just like last problem, I'm going to clear the fraction by multiplying both sides by that x minus 1 right there. On the left, 4 times x is 4x. 4 times negative 1 is negative 4. On the right, the x minus 1's cancel, and I have x squared. So just for fun, one more quadratic equation. Before we finish that, though, I just did a whole bunch of steps. Anything there murky? I know we're applying properties of logarithms. Yes. I can't just square root both sides. You're right. 4 can be square rooted, but I've got this x here that complicates things. So if I square root both sides, I'm going to now have an x under the square root. So what I'm going to have to do, since it's a quadratic equation, I'm going to put everything on the same side. So good thought. It's always good to get certain on those things like that. So I'm going to subtract the 4x. I'm going to add the 4. So I get over x squared minus 4x plus 4 equals 0. Quadratic formula always will work. The 2 factors of 4 that are going to add up to negative 4 are negative 2 and negative 2. Oh, so that saves me just a little bit of work. I've just got a repeat factor. And so then my one possible solution is going to be 2. Before I rejoice, I'm going to go up here. I've got the log base 4 of 2. That's fine. 2 minus 1 is 2, or excuse me, 2 minus 1 is 1. So I have the log base 4 of 1. That works. So it checks out. My solution is 2. Okay, so again, we did a bunch of problems. You've seen every possible look that you're going to see as far as logarithmic equations that have logarithms on one side and number on the other. Our last problem, we're each going to do one, is what to do if I have logarithms on both sides. Okay. There's a couple of different things you could do. I'm going to show you what I think is the easiest thing to do. So since you've got a logarithm on both sides, first thing I'm going to do is just like before, I am going to smush these together using my property of logarithms. So on the left, I'm going to have the log base 3 of, let me start again. I'm going to have the log, let me start a third time. For some reason, I'm stuck. Okay, log base 3, and I'm going to divide. So I've got x plus 6 over x plus 2. Brain doesn't seem to be working very good today for some reason. All right, on the other side, I've got the log base 3 of x. Difference between this problem and the previous ones, again, just to notice, is I've got logarithms on both sides. Every other problem we did had a logarithm on one side, a number on the other, so we could use the definition. Here, since I've got a logarithm on both sides, and we know, or we talked about, that the logarithm is a one-to-one function, what I can do now is I can forget about the logarithms. I can say, okay, these 2 logarithms are the same if x plus 6 over x plus 2 is equal to x. And then I'm going to clear the fraction. The rest of this is pretty typical. On the left, the x plus 2's cancel, and I have x plus 6. On the right, I have x times x plus 2, so that's going to be x squared plus 2x. Yet again, I've got a quadratic equation. I must have been in some sort of quadratic mood when I made up my examples. So I'm going to subtract the x from both sides and subtract the 6 from both sides and get 0 is equal to x squared plus x minus 6. That'll factor. Quadratic formula will work. The two factors of -6 that are going to add up to +1 are +3 and -2. That gives me two possible answers. The x plus 3 will give me an answer, or a possible answer of -3. The x minus 2 will give me a possible answer of 2. And one more time, I'm going to check both of these. So I check the -3. -3 plus 6 is 3. So log base 3 of 3. That's great. -3 plus 2 is -1. When I put the 2 in, 2 plus 6 is 8. Log base 3 of 8. When I put the 2 in right here, 2 plus 2 is 4. Log base 3 of 4. So that works right there. And so what I have is the solution set 2. All right, you have one final problem. It's the same sort of thing. You've got a logarithm on both sides, and you're going to go ahead and solve that. And in fact, I don't think that one works out to be a quadratic. So you are relieved of that. All right, just for time's sake, on this problem, it's a minus sign here, so I'm going to go ahead and use the quotient rule. And so I write the left-hand side as a single logarithm, which becomes the natural logarithm in this case of x minus 3 divided by x minus 5 is equal to the natural log of 5. Once again, since I have a logarithm on both sides and the logarithm is a one-to-one function, I can just say, okay, these two logarithms are equal if the thing I'm taking the logarithm of is equal. That has to be true because it's one-to-one. So I've got a rational equation. Fortunately, this one's not going to turn out to be quadratic, so it saves us a little time. So I'm going to multiply both sides by x minus 5 to clear the fractions. So I get x minus 3 on the left. And then I've got 5 times x minus 5, so 5x minus 25 on the right. I'm going to get all my x's on one side, all my numbers on the other side. So I'm going to subtract the 5x and get a -4x on the left. I'm going to add the 3 and get -22 on the right. Divide both sides by -4, and I get -22 over -4, which reduces to positive 11 over 2, or 5.5. So 5.5 minus 3 is 2.5. That's good. That's a positive value. 5.5 minus 5 is 0.5. So that's good. That's a positive value. Everything checks out. So my solution set can be 11 over 2.